Hello everyone, welcome to this introductory video on using the Propaceos code from Prism Computational Sciences. Propaceos, short for Prism, Opacity, and EOS, is Prism's application for generating equation of state and opacity tables for use by radiation-hydrodynamics codes like Helios and Flash, and also by spectroscopic codes like Spec3D. Prism codes are distributed with a set of pre-made Propaceos tables for a variety of elements and mixtures. But with the Propaceos application, you can create your own tables with customized parameter spaces and photon energy binning. In this video, we will create a table for plastic, a mixture of carbon and hydrogen. Let's start up the Propaceos application. First, let's add carbon and hydrogen in equal amounts. The number fractions will be normalized to 1, so we could leave them both at 1. But let's change them each to 0.5 just for clarity. Typically, we will run with detailed configuration accounting, meaning we will be calculating opacities and EOS quantities from atomic data. The tabular data option would be used for rebinning an existing table. In this example, we will use the default atomic model for both elements. If your intent is to use this table for a hydrocode, then these default atomic models are ideal for two reasons. Firstly, they include many atomic levels for all ionization stages of the element. This is important for covering the wide range of regimes spanned by broad temperature and density grids. Secondly, the atomic levels in these default models are collapsed to their configuration average. In most cases, a hydrocode will not need a highly detailed atomic model in order to simulate the radiation-hydrodynamics. We will assume LTE populations for this example. The grid parameters page is where we set up the temperature, density, and photon energy grids for our table. Symbol grids will create a given number of points on a log scale over the range given by min and max. The binning or grouping of photon energies is given here. Custom grids can also be input as tables. For this example, we will leave all these default values for the grids. Again, this coarser level of photon energy binning should be sufficient for a hydro simulation. On the other hand, if your intent is to use this table for a spectroscopy code, where spectral resolution is important, you may want to customize this photon energy grid. This may be the case if your intent is to use this table to post-process a multi-dimensional hydrogrid in a Spec3D calculation. Generally, the resolution of this photon energy grid should reflect the level of detail in your atomic model. The more clarity you have about the purpose of your table, the more intentional you can be about the level of detail, which could save you a lot of computation time, memory consumption, and final table size. If you want to create a table with EOS only, you can uncheck the Compute Opacity box. And if you want to define a separate set of grids for the EOS tables, you can uncheck this box. If we do that, we can see that this EOS tab becomes available, and then we're able to set a separate grid for EOS. There's no photon energy dependence for EOS quantities. Let's go ahead and use the same grid for both EOS and opacity. Finally, there's an option to use a QEOS model. QEOS, which stands for Quotidian Equation of State, is a semi-empirical model for determining EOS quantities near solid densities at low temperatures, where materials are in a solid or liquid state and effects of cohesion are significant. Without QEOS, the isolated atom model will be used in all regimes. PCS QEOS is Prism's implementation of QEOS, which is based on the methodology outlined in this paper by Moore et al. This field determines the number of additional density points which will be added to the EOS density grid around this specified value of solid density. Make sure you enter an odd number for this number of points to ensure that there's a point at the value of solid density. The range of these additional points is determined by this ratio value. The lowest additional point will be at the solid density divided by this ratio, and the highest additional point will be at the solid density times this ratio. This results in a higher concentration of extra points near the solid density value. The bulk modulus must also be entered. This table is here for convenience in looking up the solid density and bulk modulus values. For our run, we can find the values of solid density for polystyrene, which is an equal mixture of carbon and hydrogen. Note that this does not imply anything about molecular or crystalline structure. It is treated only as a collection of atoms. Finally, there's the definition for the region of smooth interpolation between the regimes of isolated atom and QEOS, which is defined by this parameter gamma. Gamma is proportional to the square root of ion number density and inversely proportional to ion temperature to the 3/4 power. The Propaceos documentation has more details. Let's leave it with these default values. Please note that if you're intending to use this table for a flash simulation, you may not want to use QEOS, as flash may not be set up to handle negative pressures. Let's run the simulation, but first, let's look at preferences. As with other Prism codes, running multi-threaded simulations will significantly improve the run speed, so you may want to make sure that this is checked. Okay, let's run it. This only took a minute or two to run on a machine with 16 cores. If we look in the results folder we created, the one with the PRP extension is our final EOS and Opacity table produced by Propaceos. This is what you will browse for when using this table in another application or when viewing these results later on. However, since we just ran this, we can also view the results immediately from the UI. First, let's look at the opacities. Rosland and Planck absorption opacities are plotted by default, but we can also add Planck emission if we want. Temperature and density points can be chosen down here, and if you have a mouse wheel, you can easily scroll through the values. Otherwise, you can use the arrow buttons. As temperature increases, we can see the opacity shift to the blue. Let's zoom in to see these features a little better. As we increase the density, we can also see the line broadening, smoothing out these spectral features. You can add any number of plots for additional temperature density points using this Add button. Let's go back to the main Propaceos window and look at the EOS results. In this drop-down menu, we can see all the various quantities which are part of the equation of state data. Let's look at pressure isotherms by choosing total pressure and changing the x-axis to density. We can select all the temperature values using the Shift key. This dip into negative pressures is an effect of QEOS. This is the simple representation of cohesive material strength at low temperature, high density. Let's also look at Z-bar, or mean charge. And let's look at these versus temperature. Let's change the y-axis to linear scale. As temperature increases, the average ionization increases. These plateau effects occur as the average ionization reaches a closed S shell. This S shell requires a higher temperature in order to reach that step up in ionization potential in order to continue ionizing. The plateaus occur at half-integer values, since this is a mixture of carbon and hydrogen, with the maximum mean charge being 3.5. Different densities reach these plateaus at different temperatures because the degree of ionization depends on both temperature and density. Propaceos can also be used to view already existing Propaceos tables. You can use the File menu, or you can use this icon here. Let's browse for the aluminum table in our Propaceos data location. These tables are distributed with Prism codes. Let's make a similar mean charge versus temperature plot for aluminum. For this single element aluminum case, we can see the mean charge plateau is happening right near the integer values we expect. The full ionization is right at 13, then there are 2 electrons in the 1s shell, so this plateau is right near 11, then 8 more electrons for the n equals 2 shell, and so forth. The blending occurs because there is actually a distribution of ionization levels. We can also view EOS quantities versus both temperature and density at once in a 2D plot. There is one more results window we can look at, the ion fractions window. Let's reopen our CH run result for this. We can browse to the run results folder from our previous run. For a given element in our table, we can look at the ionization as a function of ionization stage, temperature, or density. With ion stage on the x-axis, if we scroll through temperature values, we can see the distribution shift to higher ionization stages. Let's add a few other carbon lines to the plot with the Add button to see a few different temperature points together. We can also add a plot for hydrogen by changing this to hydrogen and then clicking Add again. A hydrogen distribution only goes up to ionization level 2 since it either has an electron or it doesn't. If we change the x-axis to temperature, we can see that the scannable variables are now density and ionization stage. Let's add a plot for carbon. Now we can scan through ionization stage values to see at which temperatures a given ion stage will be present. We can add a hydrogen plot here as well, and again see that it only has the 2 ion stages available. This concludes this introductory video on using the Propaceos application for creating EOS and opacity tables. Thank you for watching.